In this example, I would like to find the relative minimum of this guy, which is a function of two variables a and b here. So we can do what we did in the earlier example. I just need to find partial derivative with respect to a, set that equal to 0, find partial derivative with respect to b, set that equal to 0. And once we solve for a and b in these two equations, that should give us the location of the relative minimum that the question is asking for. Or I can just go ahead and ask Wolfram here. So I would like to minimize, and then my function is going to be 2a plus b minus 2 square. I'm going to have 3a plus b minus 11 square, and then the last term is going to be 6a plus b minus 12 square. And here we go, the minimum value is going to happen when my a is 2, my b is 1, and then the function value is going to be 26. So here comes the answer, a is 2, b is 1, and then the function value is going to be 26. Well, it turns out that this has to do with one of the earlier examples when we talk about linear regression. Specifically, back in example 3.8, we talked about how the process of linear regression is basically finding this purple line that would best fit the data point that we have. In this example, the data point that we have here is x equal to 2, y is 2, x is 3, y is 11, x is 6, and y is 12. Now then, we can think of the process of finding the purple line as finding the prediction of the value for y. I have these values for x and I would like to predict the value of y. There are two ways that we can do this, so let me actually kind of draw this here. So I knew that the value of x is going to be 2, 3, and 6. Now then, if the equation that we have is y equal ax plus b, so this is going to be my prediction. Let me actually move this lower a little bit. So this is going to be my prediction, where my a and b, this is going to be the variable here. Now, if my x is 2, my prediction for the value of y is going to be just a times 2 plus b. So the predicted value of y is going to be 2a plus b. And if my x is 3, then the predicted value for y is going to be just a times 3 plus b. So that's going to be 3a plus b. And when my x is 6, the prediction from this equation is going to be just 6a plus b. However, we also know the actual value of y. The problem said that the actual value of y is going to be just 2, 11, and 12. So then, if I want my prediction to be correct, I would like the difference between my prediction and the actual value of y to be as small as possible. You probably have heard of the term least square. Least square. So that's what we're going to be doing here. I would like my prediction to be close to the actual value here. So I would like the difference to be small. I would like 2a plus b and then minus 2 to be small. But I don't want this to be negative. So I'm going to go ahead and square that. I would like the difference between 3a plus b and 11 to be small as well. So I'm going to have 3a plus b and then minus 11 square. And then for the last one, I'm going to have 6a plus b minus 12 square. And if my prediction is good, then the sum of these three numbers should be as small as possible. In other words, I would like the square of the difference between the prediction and the actual value of y to be small. And if you look at the orange term that we have here, this is actually the same as the function that we are trying to minimize earlier. And you can notice that the value that we get, a equal to 2 and b equal to 1, this is the same thing that we get when we do the linear regression earlier. Now then, we also said that this process of linear regression is basically the same as trying to solve this system of linear equation. Let me actually just go ahead and copy this. And let me actually paste that here. Now then, we said that this thing does not have a solution because 2, 11, 12 is not in the span of these two vectors, and that's kind of what we see here. This point 2, 11, and 12 is not in the span of these two vectors, which is 2, 3, 6, and then 1, 1, 1. So there is no solution there, but the best thing that we can do is that we can find the closest point, which is 5, 7, and 13. We have seen in the earlier example that we can use the projection of the vector 2, 11, and 12 onto this plane. Well, there is another way that we can do this as well. We can look at all possible linear combination of these two vectors, which is 1, 1, 1 and 2, 3, 6, and find the one that has the smallest distance to this orange point, which is 2, 11, and 12. So, let me actually move this further down. Back in example 7.6, we use the method of projection to find the closest point. But let's say that I would like my vector in the span, which is 236 times A plus 111 times B, to be as close to this guy as possible. So I would like for these two vectors to be as close as possible. But if I write down my left-hand side, I'm gonna have 2A plus B, and then I'm gonna have 3A plus B, and then the last one is gonna be 6A plus B. Whereas my right-hand side, this is gonna be just 2, 11, and 12. I can find the difference between I can find the distance between these 2 points, and that is gonna be just 2A plus B minus 2. I just have to subtract the coordinate between the two. 2A plus B minus 2 squared plus 3A plus B minus 11 squared. 3A plus B minus 11 squared. So this is just the distance formula without the square root. And the last one is gonna be 6A plus B and then minus 12 squared. And we indeed have arrived at the same equation that we have from earlier. So this is another way that we can look at what really happened behind the scene of linear regression.